So just like I was saying, the dy on dx is the notation introduced by Leibniz. It's not actually a fraction because, again, these aren't actually real numbers. For right now, the technical sense is that this is just a different way to write the quantity f prime of x. So when I look at this dy on dx, I should be thinking of it as the limit of the difference quotient. And here we've written the difference quotient in terms of our deltas. So remember that capital delta of y is just measuring change in y. That's my f of x plus h minus my f of x. I'm dividing by, well, delta x is just going to be h. Again, I like to think of this as my Greek letters are telling me the macro level of things, the big pieces, and the Latin, the dy, the dx, those are what would be happening in the infinitesimal realm, you know, if we could actually get our hands on that. That's what the limits are for. Now, because the derivative is a function, right? Different x coordinates give me different slopes, so the derivative of a function has to be a new function. Sometimes I will want to talk about the derivative at a specific coordinate. And with this notation, it's not immediately obvious how to do that. So if I have this quantity dy on dx, and I want to evaluate it at a particular x coordinate, call it a, the way I'm going to do this is introduce a vertical bar, and then at the bottom of that vertical bar, I'll write in x equals a. This notation is standard, but it's probably less useful than just writing f prime of a, right? We have this very nice notation for functions. We might as well use it. So this f prime of a says, calculate the derivative of the function f, insert the number a for every time the variable x appears. Tell me what you get. So as I've been saying, every single time when I take the definition of my derivative, the derivative is equal to such and such limit if that limit exists. Now, we will be seeing some functions whose derivatives don't necessarily exist everywhere. There might be some coordinates where the function's derivative doesn't exist. You could think of this as coordinates where there isn't really a slope of a tangent line we could define. There's a couple different reasons that could happen. Perhaps the function comes to a sharp corner and we can't define a tangent line that way. Or perhaps we found the tangent line, but the tangent line is completely vertical. A completely vertical slope is undefined. So what we'll say is that the function f is differential at a if that derivative does exist. So I can calculate my limit. I try the coordinate x equals a. If that limit actually exists, I'll say that the function f is differentiable. Alternatively, if it doesn't exist, I'll say it's not differentiable at that coordinate. I'll also want to talk about functions whose derivatives exist in some interval. For technical reasons, I can only talk about differentiability on open intervals, right? Remember, my limits need to exist coming in from both directions. So I need to have a little bit of room on both sides of my coordinate. So if that derivative exists for every single point in the open interval, let's say from a to b, finite interval, or maybe one of my infinite intervals, infinite on the right, infinite on the left, or the entire number line. If my function f is differentiable at every x coordinate in that open interval, we'll just say it's differentiable on the interval, right? This function is differentiable everywhere. That function is only differentiable between 1 and 2, stuff like that.